Då har vi kommit till projektet som vi ska få höra mer om idag. Det har letts av Shareq, Mohd, Nazir på KTH och det har varit övriga deltagare från KTH, Chalmers, från CIT Industriell Energi och från Pontus Energi. Projektet avslutades här faktiskt i januari, inser jag nu, det står fel här, det pågick i januari också. Och finansiärer, förutom Energimyndigheten och FTS-parter, har varit de medverkande Chalmers, KTH och Pontus Energi. Och man kan läsa mer om projektet på projektets webbplats, som det finns en länk till här. And by that I will switch to English because this presentation from Shareq and Pontus Bokinge here today will be in English. So I will stop my presentation and Shareq, please share your presentation and you're very welcome to start. So then you have to unmute yourself, Shareq.
Oh yes. Can you see my screen now?
Yes, you can see it.
Okay. Can I begin?
Yes,
Ingrid?
go ahead, please.
Okay. So first of all, good morning, everyone, and welcome to our presentation. We're presenting the results from the project we carried out in the last 1.5 years or so. The project is titled in English, Routes for Production of Transportation Fuels via Deoxygenated Bio-oil. It's a collaboration between KTH, CIT, Industriell, Energi, Chalmers, and Pontus Energi AB. And I also have my project partner, Pontus Bokinge, from CIT Industriell Energi, who will be presenting half of this presentation. So let me just start here. So the outline of today's presentation, we'll discuss a little about biofuels in transportation, mainly in Sweden. We are going to discuss about about using hydrogen in producing the drop-in fuels or transportation fuels via deoxygenated bio-oils. We'll also discuss the process performance for different hydrogen generation methods when they are integrated with biofuels production. Pontus then will present about the economic and greenhouse gas assessment for the processes that we have studied, and then we'll summarize and have some conclusions from our results. So let's start here. When we speak of biofuels in the future transportation system, let's go back and take a step back. And Sweden has a long-term goal to achieve net zero emissions by 2050. And then biofuels are going to play an important role in it. In this target, one of the milestones is to reduce the greenhouse gas emissions from domestic transport by 70% by 2030, with respect to the levels in 2010 in Sweden. And the other aim is also to have a blending of jet fuels, around 27% blending of jet fuels with biojet fuel by 2030. Currently, biofuels account for 19.5% or 16 terawatt hour per year of energy in the current energy mix. But to achieve the 2045 targets, this is predicted to increase to 38 terawatt hour per year. So more than doubling of the throughput of biofuels when we compare it to the current scenario. And then the production of hydrocarbon-based drop-in fuels in transportation, such as petrol and diesel from residual biomass, provides us with the possibility of utilizing the existing industrial process that are there for fossil-based fuels right now. It also helps us utilize the existing distribution networks of the fuels, and it is also compatible with the existing vehicle fleet. So this is a small background to the project. When we speak of processes for producing deoxygenated bio-oils that can then be used to produce transportation fuels, we start off with biomass on the left. That is sent to the pyrolysis step, where it is pyrolyzed to produce pyrolysis vapors and biochar. The pyrolysis vapors are condensed to form crude bio-oil, and then the non-condensable gases are separated from the crude bio-oil. And this crude bio oil has got 34 to 40% of oxygen that needs to be removed before this bio oil can be sent into a refinery to generate transportation fuels like gasoline and diesel. And this is done in a hydrodeoxygenation step. When we say hydrodeoxygenation, it is using hydrogen to remove the oxygen content in the crude bio oil. So your hydrogen reacts with the oxygen to form water, and then the remaining is the hydrocarbon, which is the deoxygenated bio oil here on the right. And then you separate the water from the deoxygenated bio oil, and you send the deoxygenated bio oil to refinery to get different transportation fuels in the form of gasoline and diesel. The important thing to notice here is that the amount of hydrogen that we will require to deoxygenate the bio oil, and we need close to 50 to 200 kilogram of hydrogen per ton of crude bio oil entering the hydrodeoxygenation step to generate the deoxygenated bio oil. And when we speak of the amount of hydrogen that we'll require to achieve the 2045 climate targets in Sweden, we would need anywhere between 0.17 to 0.42 million tons of hydrogen per year in the HDO step to achieve these climate targets, which is quite a lot. And in this project, we have been then focusing on how best we can get hydrogen into the system or into the hydrodeoxygenation step. This picture can be overwhelming, but I will try to break it down into smaller pieces. So what we saw in the previous step was the pyrolyzer, which is here in the heart of this process. So your pyrolyzer process your biomass to produce biochar and crude bio oil and also non-condensable gases. This crude bio oil is sent to the hydrodeoxygenation step, and then the crude bio oil is hydrodeoxygenated. Your deoxygenated bio oil is then sent to the refinery to produce different transportation fuels. So this is the process in the center. And then what we looked at in this project is how best we can get the hydrogen into the system or into the hydrodeoxygenation step. And then we looked at four different processes of producing deoxygenated bio oil. We looked at if hydrogen comes from the electrolysis step. So that is in blue here, in this blue bracket. So you're using renewable electricity in the electrolysis process to generate hydrogen, and that hydrogen is used in the hydrodeoxygenation step. The other process that we looked at is if this hydrogen comes from natural gas. Now, instead of natural gas, we could also consider it could come from biomethane or biogas. But in this project, we mainly looked at producing hydrogen from natural gas. So natural gas is sent to a steam methane reforming process, and you get hydrogen from the process, and that hydrogen could be used in the hydrodeoxygenation step. The other process we looked at is using biomass gasification. Your biomass is sent to a gasifier, which produces a producer gas. We have some gas cleaning and upgrading steps to generate hydrogen, and this hydrogen could also be used in the hydrodeoxygenation step. So that is shown in green here. One important advantage of using biomass gasification is we could also use the biochar that is produced in the pyrolysis step here in biomass gasification to generate hydrogen for the HDO step. The final process that we also looked at in this project is the integrated hydropyrolysis and hydroconversion process. What we have here is instead of adding hydrogen to the hydrodeoxygenation step, we already add hydrogen to the pyrolysis step. So we have a hydropyrolysis step here. So you have biomass entering along with hydrogen into the hydropyrolyzer. And then what we have here as a product is partly deoxygenated bio oil, which is in vapor form, which is sent into hydrodeoxygenation step, where we do not have to add additional hydrogen, but then the residual hydrogen in the stream reacts with the remaining oxygen content in the vapors to generate deoxygenated bio oil directly. And the remaining non-condensable gases are sent to a reformer to generate hydrogen again that is sent to the hydropyrolysis step here. So here we have integrated the HDO step and the pyrolysis in the single reactor, in the hydropyrolysis reactor. The other thing that we looked into in this project is instead of looking at instead of condensing the pyrolysis vapors to have crude bio oil, which is sent to the hydrodeoxygenation step. In this project, we looked at directly sending pyrolysis vapors into a vapor phase hydrodeoxygenation step. So you have biomass entering pyrolysis step, you have biochar and pyrolysis vapors, and this pyrolysis vapors have got a certain oxygen content that we need to remove, and we add hydrogen directly to the vapor phase hydrodeoxygenation step. What we get is we get crude vapors out, which we condense, and we get deoxygenated bio oil and water that we can separate, and we also get non-condensable gases from the vapor phase hydrodeoxygenation step. And then this deoxygenated bio oil is again sent to refinery to generate transportation fuels. So our focus in this project has been on vapor phase hydrodeoxygenation step. One of the main reasons for us to consider this process is because we can do this at atmospheric conditions. We do not have to have high pressure hydrogen going into a hydrodeoxygenation step, which would be the case for liquid phase hydrodeoxygenation step, where we sent in hydrogen at 200 bar. In this project, we studied different process scenarios, as we discussed in one of the slides before. We studied if the hydrodeoxygenation step uses hydrogen generated from natural gas reforming. We studied if hydrodeoxygenation step utilizes hydrogen generated from electrolysis, hydrogen generated from biomass gasification, and the other integrated biomass gasification step, where we try to utilize the biochar generated from pyrolysis step in the biomass gasification process. We also studied a couple of other additional cases where the CO2 generated from the system, if that is captured. So we studied two cases where we have CO2 being captured from the natural gas reforming process that is generating hydrogen for the HTO step. We also studied CO2 is captured from combustion exhaust gases from both pyrolysis and gasification step in this process, which is the IBG process. And then we have the IH2 process, which is the integrated hydropyrolysis and hydroconversion step to produce bio-oil. The key performance indicators for process performance, to study the process performance, we had system level carbon recovery, which shows the mass of carbon in the bio-oil with respect to the mass of carbon input to the entire system. The second KPI for us was to see the system level yield of bio-oil, which is the mass of bio-oil produced with respect to the mass of dry biomass feed to the system. And finally, the system level conversion efficiency, which is the total output energy, both in terms of fuels and steam or electricity, divided by the total input energy, which is coming mainly from biomass, electricity, or heat. These are the important results from the project. In the blue bars here represent the carbon recovery. The orange bars represent the yield, which is the mass of bio-oil produced with respect to the mass of dry biomass inlet. And the gray bars here represent the efficiency or the system level efficiency of the process, which is total energy in divided by total energy out divided by total energy in. As we see here, for different cases, the IH2 process, which is your integrated hydropyrolysis and hydroconversion process, outperforms all the other processes in terms of carbon recovery, the yield, and efficiency. One of the main reasons here is the IH2 process is designed at a pressure between 20 to 25 bar, and so relatively higher pressures favor requires higher hydrogen consumption, but then lower CO2 formation, and that's why we see the carbon recovery in the IH2 process is higher than the other process studied here, because all the other processes are at atmospheric pressure. In the process based on natural gas and electrolysis, we see that we have higher carbon recovery and yield compared to the biomass gas, the process using biomass gasification, mainly because in natural gas and electrolysis process, we do not add any additional biomass for hydrogen generation, but rather I think here we add natural gas and here we have electricity for hydrogen generation. Whereas in biomass gasification, we have to add additional biomass to generate the hydrogen that is required for the hydrodeoxygenation step. What we also notice here is that applying CCS results in a decrease in the efficiency of the total efficiency of the process by 4 to 5%. We observe that here. If we compare the natural gas process with the natural gas process with CCS, and we check the efficiency, which is the gray bar, there is a dip in efficiency by 4 to 5%. And similarly, if we compare the IBG process here and the BECS process applied to the IBG process, there is a dip of the total efficiency going down by 4 to 5%. We haven't studied if we apply CO2 capture to the IS2 process, but we can make an estimation that the dip in efficiency would also be close to 4 to 5% in the IS2 process if we capture the CO2. The other thing that we also noticed is that the carbon recovery in the IS2 process is the highest, which makes us believe that improving carbon recovery should be one of the focus in future research activities when we are working with biofuels production. With this, I leave it to Pontus now.
Okay, thank you, Shareq. Oops. Did you give me the control of the presentation?
Yeah, I think you'll have to click once on the slide.
Yeah. Yes. Try to get that working. Okay, yeah. Thank you. Okay, hello everyone. I will say a few words about the climate and economic performance of these investigated production concepts or production pathways. And both of these aspects were evaluated based on the feedstock and energy demand of the processes that were determined by the process modeling that Shareq and his team did. And for the economic performance, we have not actually made a detailed CapEx estimate of a production plant, but instead I will show a comparison of estimated operating costs of the plants and possible fuel revenue, and then the difference between these parameters give an indication of how high the investment cost can be while still allowing the plants to be profitable, and this can give a first indication of economic performance. Talking about greenhouse gas emission consequences of biofuel production and use, these feedstock and energy demands that were determined in process modeling were combined with CO2 emission factors describing energy gas consequences of supplying the inputs to the production plants, as well as emissions at the production plant and when the fuel is used. So the climate assessment here is a well-to-gate plus combustion assessment that includes emissions at the plant and upstream of the plant, as well as in combustion of the fuel, although combustion of biofuels or biogenic carbon was considered to generate or to have an emission factor of 0, of course. Now, since we're looking at developing production concepts that are not yet commercialized, we have based both energy prices and greenhouse gas emission factors on future scenarios for 2030 that were developed using a tool called ENPAC that I will describe on the next couple of slides here. And the ENPAC tool was developed by researchers at Chalmers to construct energy market scenarios for timeframes up to 2050. And this tool uses as its basic input the International Energy Agency's price projections for fossil fuels on the European markets, and then combines this with an energy market model to determine consistent prices for electricity, biomass, refined fossil fuels, and heat. And the model also calculates CO2 emissions associated with a marginal increase in the use of energy and biomass. So the calculation of CO2 emissions considers the marginal long-term consequences of increased usage of an energy carrier. So for example, if increased use of electricity leads to a further rollout or development of wind power, then the CO2 emission consequences of using more electricity will be considered very low, even if the sort of average grid emissions can still be higher. This marginal concept used in ENPAC also has major implications when evaluating the use of biomass. So in these future scenarios, we can either consider biomass a limited or an unlimited resource. And if biomass is considered unlimited, then biomass availability exceeds demand, and there is an excess of sustainably available biomass that can be used with very small direct CO2 consequences. However, if we in a future scenario consider a case where all sustainably available biomass is already utilized, then using biomass for biofuel production will divert it from some other use. So for example, if a new biofuel plant uses biomass that was previously used for power production, then the marginal effect of that can be increased use of coal for power production, for example, leading them to very high CO2 emission consequences of that marginal use of biomass. So this picture is important to have in mind when we look at some of the results later on, because in the evaluation of climate and economic performance, we have used two different ENPAC scenarios for 2030. We have used one new policies scenario, which is where input data to ENPAC is based on currently announced policies on the green energy and climate area. And then we have also used a sustainable development scenario that is based on the clean energy policies that would be required to keep global warming well below 2 degrees or in line with the Paris Agreement. And in this sustainable development scenario, biomass utilization can be expected to be very high, and we have considered sustainably available biomass to be a limited resource in this case, while considering it an unlimited resource in the new policies case. Other important differences between these scenarios is that in the new policy scenario, we have generally lower biomass prices and a lower CO2 charge, while these factors are higher in the sustainable development scenario. Moving on to the results and starting with the economic assessment, I will show a comparison of plant operating costs and fuel revenue to give an indication of investment opportunity. And in this figure here, the bars show the operating costs of the various production concepts that Shareq described in the new policy scenario. So that is the scenario with lower biomass prices and lower CO2 charge. In the graph here, the white diamond shapes show the total operating costs of the plant, while the dashed line gives the projected fuel sale price at gate. So starting from the left, the two natural gas cases and the electrolyzer case actually have higher operating costs than the fuel sale price, meaning a production plant cannot be profitable. And in the cases based on biomass gasification, operating costs are lower than the fuel sales price, but the difference is too small to support a plant investment, especially if a reasonable operating margin is required. And in this BECCS case, so the biomass gasification with carbon capture and storage, the negative emissions have been assumed to generate a profit related to the charge for emitting fossil CO2, but in this case, this charge is not high enough to offset the added costs of the capture process. Only this much more efficient integrated IH2 process achieves operating costs that are low enough to support an investment in a production plant while also maintaining a healthy operating margin. In all the pyrolysis cases, that is the 6 cases to the left, the supply of biomass, that's the green parts, and the supply of hydrogen, the yellow parts of the graphs, are the main cost drivers here. And the cost for hydrogen then is based on the cost for biomass, power, or natural gas, depending on the production concept used. And it's clear here that the hydrogen demand should be sharply reduced to allow profitability in the pyrolysis cases. If we look instead at the sustainable development scenario, we have higher biomass prices, so higher production costs in most cases, and also the CO2 charge is higher. So total production costs go up in most cases. However, the high CO2 charge, sorry, now I looked at the chat, got off track a bit, but okay, so we have higher CO2 charge in this case, so this sort of negative emission credit assumed for the bioenergy carbon capture case, that actually produces quite a lot of revenue for the plant and decreasing production costs in this case, but still not enough to be able to support an investment with this production concept. If we move on to the results for the greenhouse gas emission assessment, I will show the calculated emissions of the analyzed production concepts and compare to fossil diesel. The results for biofuels and fossil fuels include emissions at the fuel production plant and upstream of the plant, and also the emissions from combustion of the fuel, although biofuel combustion emissions were set to 0. Starting with the new policy scenario, where we assume that the global availability of sustainable biomass exceeds the demand, all the production pathways except the ones based on natural gas achieve good emission savings compared to the fossil comparator. And this is especially true for the electrolyzer, the IH2 pathways, and in particular the bioenergy CCS pathway, which achieves negative emissions due to the carbon capture. The dashed line here indicates the 65% reduction required for fuel to be calculated towards targets of the Renewable Energy Directive. And the results indicate that most production pathways should be safely below this limit, although it should be noted that the RED II methodology differs from the methodology used for this graph, especially in the electrolyzer case. And finally, if we look at this sustainable development scenario where we assume that all sustainably available biomass is already utilized, then the utilization of biomass for biofuel production will displace it from some current use. And in this case, the marginal user is co-combustion with coal in power plants, meaning that increased biofuel production will also ultimately lead to increased coal combustion. And in this scenario, all investigated pathways give very high emission consequences due to a comparatively low utilization of the carbon in the biomass that is then better utilized for power production in this case. However, it should be noted, of course, that this is far from the situation today where there are still large unutilized biomass resources. And with that, I give the word back to you, Shareq.
Thank you, Pontus. So if we have to summarize what we did in the project, right, what we studied was the techno-economic environmental performance of transportation fuel production via deoxygenated bio-oil and integrated with different hydrogen generation process. The integrated hydropyrolysis and hydroconversion process, which is the IH2 process developed by the Gas Technology Institute and Shell, it outperforms the other process routes techno-economically. The hydrogen generation process and its efficiency has a significant impact on the system level carbon recovery, system level yield and system efficiency. And I think we saw also in the results from Pontus that it also has an impact on the costs. The electrolysis is a better route to generate hydrogen for the HDO step with respect to just the system level carbon recovery. When you speak of integrating CCS, it reduces the efficiency by 4 to 5 percentage points. However, in the scenario with incentives for negative emissions, integrating BECCS makes biomass gasification route for hydrogen production very attractive. But again, it depends on the scenarios that we are looking at or the policy scenarios that we're looking at. What we noticed is more than 50% of the carbon is actually lost in the form of CO2 when we produce biofuels, and I think in that case, then CO2 utilization can enable improvements in carbon recovery when we're discussing biofuels production. And what we also noticed is there's still very limited amount of literature available out there on biofuels production. I think further research is required in hydrodeoxygenation process. One of the process that we could, or a couple of processes that we can also analyze and probably report in the articles that we are planning in the future is what if we use biomethane instead of natural gas to generate hydrogen, and the other one would be applying CCS to the IH2 process. With that, I think we come to the end of the presentation. So thank you, everyone.
Thank you very much, Shareq and Pontus, for your presentation. Very interesting. So during the presentation, we got one question in the chat. The question was, what is the basis for OPEX for CO2 capture and storage? Do you have a comment on that? I think Pontus is the one who has these numbers.
Yeah, sure.
Before that, Ingrid, is it okay if we stop sharing the PowerPoint?
Yeah, please stop sharing your presentation.
Thank you.
And if it's something we want to look at, we can share it again. So.
Okay. Yeah. So that OPEX estimate is based. That's based on the Northern Lights project and their OPEX estimate for 2030 for the transport and storage part. I don't remember the exact number. I think they give an interval of 30 to 50 euro per ton. We've used the midpoint of that.
So, yeah, thank you. Just to let you know, now during the question and discussion part, please feel free to raise your hand, and you can ask your question yourself. If you prefer, you can write it in the chat, and then I'll ask the question instead. But it's open for everyone to ask. So we had another one in the chat. What is the mean H2 price used in the electrolysis case? Also for you, Pontus, I think.
Yeah. So we actually don't have a hydrogen price per se, but we have prices for the inputs that are used to produce hydrogen. So that can be electricity, biomass, or natural gas, depending on the production pathway. The electricity price is 45 euro per megawatt hour. And then the efficiency of the electrolyzer, I can pass that to Shareq.
Yeah, so what we considered there was an alkaline electrolyzer which Nel is selling. It's the best technology that they have for hydrogen generation. I think it produces 8 tons per day capacity per electrolyzer with 99.9% purity and 42 kilowatt hour per kilogram of hydrogen produced. So these were the numbers that we used.
Yeah. Okay, thank you. We have a question here from Monica Johansson. So please, Monica, go ahead and ask your question.
Yes, thank you. And thank you very much for this nice presentation. I am representing the Volvo Group, and as you know, we are using a lot of diesel today. So I was just wondering, because I didn't get it, if it's the final fuel, is it diesel or is it some other fuels, or is it a drop-in or a diesel, or does it fulfill this diesel standard? I didn't get this in the presentation.
It's a gasoline diesel split, but for the details, I have to pass it along to Shareq.
Yeah, so the crude bio oil, right, that is going into the refinery, or the bio oil, the deoxygenated bio oil that is going into the refinery, we have considered that it has only carbon and hydrogen, which with 86 to 87% carbon, and the remaining hydrogen by mass.
But I mean, for this economical study and this greenhouse gas, is it like diesel used in a vehicle, or is it going into the refinery?
No, it is the diesel used in the vehicle, if I'm not wrong.
Okay.
Yeah.
Thank you.
Okay. We had a question in the chat again. Sometimes I got lost in the technical parts of the presentation. So what is the conclusion of the project? Is it correct understood that the process is feasible from both a technical and economical aspect?
I'll answer on the technical aspects or the process performance side. I think, yes, it is feasible, especially the IH2 process, right? That is a great leap in terms of biofuels production. And it shows an efficiency of 60%, the system level efficiency, whereas the other processes have somewhere around 25-30%. But of course, in terms of research, there is still a lot to do. But in terms of the feasibility, yes, it is feasible. Especially the IH2 process, it has been proven.
Yeah, and from an economical point of view, the IH2 process also looks like that could be economically feasible. But the other process concepts that were investigated here based on the pyrolysis pathway, they look quite far away from being economically feasible at this point.
Yeah, so my conclusion from listening to you and reading about your project was that this integrated hydrogen process seems very interesting. Because it shows best performance in various aspects. And what do you think? We said further research is needed, but what do you think is necessary to move to the next step in the end to get it commercialized? What do you see is needed when it comes to that process?
I think first of all, right, at least the way I see it, we need to optimize this process for the kind of feedstocks that we have probably here in Sweden. I think that is important, understanding how our feedstock responds to the IH2 process. On the other side, the normal pyrolysis steps, right? I think that there is also scope of improvements there, especially because what we have analyzed is all the process atmospheric conditions or atmospheric pressure, sorry, not conditions. And what happens if we pressurize the system then? Do we have an improvement in efficiency even in those processes? And how much is it? Is it comparable to the efficiency of IH2 or not? And the other thing that we also notice is the carbon recovery. Even in the IH2 process, it is around 45% in bio-oil, and all the remaining carbon is actually lost as CO2 from the process. So how can we improve upon that? That is one more step, I think, to look at.
Yeah, so what would you, if you say it on turn around a little bit and say, so what would you say is the main drawback with this integrated hydrogen process?
The main drawback.
Maybe there are no drawbacks. I don't know.
I mean,
but
among the processes that we studied, right? I mean, we don't see a drawback in the IH2 process.
So no drawback at all. Yeah. So someone else who has a question, please write in the chat or raise your hand. Then I'll continue a little bit. Something, if I understood correct, the biochar that is produced in this process that you looked at, you use it for gasification, and but sometimes you use the biochar for like a way of carbon storage or other. Have you looked into that sort of scenario and how that will affect?
No, but this is an interesting point.
Yeah.
Because especially where we are not having biomass gasification, right, for hydrogen generation. Let's assume we have it only from electrolysis. Then I think it would be interesting to look at how much carbon we can negate by using biochar as a soil amendment measure. Yeah. No, we haven't looked into that, but thank you, Ingrid.
Interesting way to continue. Yeah.
I think we have one more question regarding the IH2 process.
Is it something that I missed? Okay, I'm sorry. Thank you for clarification. I missed the beginning. Is the integrated hydrogen process owned, patented by a certain company, or who is the owner of the process? Yeah, that was an interesting question too. Who owns the technology?
So it is a Gas Technology Institute that developed the process technology, and I think Shell has licensed it, if I'm not wrong.
Okay.
I can repeat it. Yes, it is the Gas Technology Institute, GTI, and Shell company. Yeah.
So you think it's Shell who owns the technology today, but it's GTI who developed it.
Yeah.
Yeah. Have you looked into any sort of sensitivity analysis here? Is it some of your assumptions that would heavily influence the results or the conclusion of the results?
I think with respect to the process performance, right, the only parameter that we could have played around with was the amount of hydrogen input to the hydro deoxygenation step. Because higher the hydrogen input, we have a higher amount of bio oil production from the process. But it is not, but the curve saturates after a point, and we do not get a very high, what do you say, improvements even if we add higher amount of hydrogen. So we did look at that in the sensitivity studies.
On the cost side, is it any of the costs that are?
No, not really. Not beyond the two different scenarios. But of course, it's very sensitive to various input prices. And especially today, it's quite difficult to tell what will happen with energy prices in general.
Yeah, it is.
Yeah, I think in this project, right, we had different feedstocks, so it also depends on the price of different feedstocks. So I think we can consider doing a sensitivity for the price of, for example, natural gas or biomethane, or the price of electricity, or the price of biomass itself. But we have not shown that in this presentation.
So someone else who has a question? Oh, it's quiet. We talked a little bit about the future for how to continue with the integrated hydrogen project, but will you continue this work in any way? Do you have any plans for further research related to this project?
Yes, especially we want to study a bit more about the vapor phase hydrodeoxygenation process, because it looks interesting to start off, because we do not have to pressurize the hydrodeoxygenation step. And also we could use the vapors from pyrolysis step directly into the HDO step, instead of condensing the crude bio oil and then pressurizing the hydrogen and then utilizing in the HDO step. So we are looking for opportunities to work on or do experiments mainly on this topic, because what we feel is we lack a lot of experimental results on vapor phase hydrodeoxygenation, and there have been recently a couple of publications in that regards, but not much. So that's one topic that we are planning to develop.
Cortus Energy, who has been part in this project, I don't know if we have someone from Cortus here listening today, but do you know if Cortus Energy will continue take this further in any way?
I think so. I think the important thing for quotas, as we discussed during our project meetings, was the bio oil yield, which is the amount of bio oil produced with respect to the total biomass input. So I think improvements there will probably be helpful for them going forward. So, and that again depends how best we utilize the hydrogen to deoxygenate the pyrolysis vapors.
So thank you. Any more questions? It's quiet in the audience. Yeah, what type of biomass is used? Solid or liquid? It's solid biomass, right?
Yes.
But have you looked at different composition of the solid biomass?
Yes, we did that. So we actually had in the report for different types of pine, at least 4 different types of pine and spruce, which is mainly found in Sweden. But then the kind of composition, right, is also very similar to sawdust, and that makes it. I mean, that makes this kind of process technology a very suitable option to be integrated with sawmills, for example, where you have sawdust already, and see if you can use sawdust to produce transportation fuels. So we looked at different biomass types. The cellulosic content, of course, has an effect on the amount of bio oil being produced. Yeah.
Yeah, now we have a question regarding the Cortus process. What conclusion could be made from the Cortus process? Was that feasible from a technical point, but not from an economical point? And how did it compare to the integrated hydrogen process?
I think for now it is less than the IH2 process, because even in terms of the bio oil yield, right, in the hydrogen, in the IH2 process, we have close to 45% of the yield. 27 to 30% yield of bio oil with respect to biomass. But I think in our process, we were only able to achieve 21, 22. And that is an improvement that we have to probably target. But I didn't understand the question properly. Like what conclusions could be made from the Cortus process? Like what is the Cortus process? I don't know. It is the general pyrolysis process. So
yeah.
So from a technical point of view, we still see that there is scope of improvement, if that is the question. And it has 4 to 5 percentage points less than the IH2 process in terms of the bio oil yield.
It seems like he said thank you, so it seems like you are satisfied, Simon. So by that I don't have any further questions from my side. So if there aren't any more questions from the audience, I think we can wrap up here. But I give a few more seconds if someone wants to raise their hand. Your last chance is now. So a big thank you for your presentation and very interesting results, Shareq and Pontus, and thank you for listening and asking interesting questions today. So thank you very much, and I hope to see you on the next webinars coming up here in May and June. Goodbye.
Yeah, thank you.